Today we are see the new topic, that study of D block elements. I am Dr. S.P. Deshmukh, Department of Chemistry, DB of Dayanand College of Arts and Science, Solapur. So first of all, we have to aware about the periodic table. So we are not going in detail how periodic table playing major role. There are having S block element, P block, D block, F block elements. But out of that, we mainly focus on DO block elements because the D block elements having its wide range of applications. So in this case, the elements why we call as a D block, because their outermost shells are filled with a D orbital, or that we call as a filled D subshell with respect to main shell, and it is having transition between the S and P block elements. And its also property lies in between S block elements as well as a P block elements. Then we have to see the different series, that is a 3D series, 4D series, 5D series and 6D series. So D block elements we call as the transition elements, and their outermost valence electrons are present in D orbital as well as in S orbital. In 3D series, there is atomic number from 21 to 30, 4D 39 to 48. For 5D and 6D, there is a starting lanthanide series and actinide series, that is a 57, and for actinide 89, but 57 and afterwards 72 to 80 for 5D, and for 6D 104 to 112, like to be that way. These are the 4 series consisting of D block elements. Then we have to see its electronic configuration. So first transition series, in which outermost electronic configuration is a 3D 1 to 10, 4s 1 to 2. So elements are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So atomic number from 21 to 30. It's a general electronic configuration. It starts that 3D 1, 2, 3 up to so on up to 10, but there is having some exceptional example in which chromium it used to be 3D 5 4s1, while for copper 3D 10 4s1. That would be happen due to there is a half filled and completely filled orbital are more stable, and therefore shift of electron would be takes place. Then question is there are having some common oxidation state, generally +3 oxidation state, +4, 5, +2. In maximum oxidation state for the manganese, +2, 3, 4, 5, 6, 7. And that way we have to get the idea about the how that 3D series would work with respect to its electronic configuration. For the 4D series also, there is having elements like deuterium to zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium from atomic number 39 to 48 with having different symbol, and its electronic configuration from 4D15s2 up to 4D10s2. Also there is having there is an abnormality in the electronic configuration for the some elements we have to see here. Then for third transition series, that is a 5D from lanthanum, hafnium, tantalum, then tungsten, rhenium, osmium, iridium, platinum, gold and mercury from atomic number 57, that is afterwards 72 up to 80, with having this electronic configuration 5D 1 to 10 for 6s 1 2, with having such type of electronic configuration. So we have to see actually what are its general characteristics, in which first of all oxidation state, they have to show very common oxidation state, that is a +2 and +3. For the copper it show the minimum oxidation state, that is a +1, and for Mn +7 it is having maximum 1. So stability of +2 oxidation state increases from scandium to zinc, while its +3 oxidation state stability goes on decreasing from scandium to zinc, while stability for the D0 case, D5 case and D10 case, because empty orbital, half filled orbital and full filled orbital. Then in case of oxidation state, we have to see there is a having lower oxidation state, which is equal to they act as a reducing agent and they are basic in nature. So Fe plus 2, chromium plus 2. While higher oxidation state are oxidizing agent, also they are having examples which Mn2O7, CrO3. There are having some common oxidation state that can show the amphoteric nature, MnO2 and Cr2O3. So these are the some characteristics in which color also playing major role for the transition elements. So here the example of exact wet titanium plus 3, in which oxidation state of plus 3 of titanium, which leads to DD transition, and there is a having a color observation due to different way. One we call as a DD transition, another one is the charge transfer transition, and there is a having metal to ligand transition or ligand to metal transition, and they have to show the complementary color of absorbed radiation. So complementary color, suppose green radiation is absorbed, then we get the purple color. So here exact wet titanium, in which D1 case where electron present in T2G goes in excited state by absorption of light into EG, and during that process they have to absorb the complementary color, and we observed it's a opposite color. So that way they have to show the color due to absorption would be takes place in its visible region. So these are the some different elements with having different oxidation state show the different color. So why these color? So tantalum plus 3, vanadium plus 2 plus 3 plus 4 plus 5, then chromium plus 2 plus 3 plus 6, the manganese plus 2 plus 7. So these different colors with having different oxidation state of the same elements. So it indicates that the presence of electron in that orbital show the absorption in its visible region with having different wavelength, that is a complementary color, and we get it. So for the D0 case, vanadium plus 3, titanium plus 4, it is colorless. Copper plus 1, D0, D10 case colorless, while in between D1 to D9 they have to show some color. So it indicates that the absorption would be takes place due to presence of unpaired electron in its visible region. Then another characteristics, what are the factors mainly responsible for the color of the complexes? So there are different factors, majorly whatever the electron present in d orbital. Second one is whatever the geometry of the complexes. So it is having different geometry. So these are the different geometry, and that geometry playing important role for the absorption of light in its visible region. Then next one is what are the strength of the field, strength of the ligand. So strong field ligand, weak field ligand, that also playing major role for the show the that is a strong field ligands or weak field show the high spin complexes, low spin complexes, which lead to absorption in visible region. And next one is having defect in solids. So the defect like the Schottky defect, Frankel defect, color centers, they also playing major role for the different coloration. So these factors are mainly responsible for the color of the complexes. Thank you so much.